Okay, the next talk is going to be underwater. So very exciting to read the title. It's a very long title. I'm not going to entirely repeat it, but I think it's a very exciting talk. And over to you.
Yep. So thanks for the introduction. It's a pleasure for me to be here. I want to take this chance to thank the organizing committee, the program committee, and also you guys for this chance to tell you about our research. So I'll get started. This is a brief outline. I want to go through the motivation, why are we doing this study, some background, what's other research that has been done which is similar, the development that we did. We developed a headset for use underwater and also some software, and then we did a user evaluation and then some discussion. So as you know, astronauts are, sorry, you guys didn't see that. That's the outline. So I'll start off with the motivation. So as you know, astronauts are occasionally required to exit the spacecraft, go on the outside of the spacecraft, and this is called the spacewalk. And this is a really challenging task, right? So here you see the space station. It's actually floating over the South Island of New Zealand there. Astronauts are wearing these bulky spacesuits. It's difficult for them to maneuver, and they're required to do very kind of complex tasks. And So NASA trains the astronauts before they get into these environments, because if something goes wrong, it can be really bad. So you guys have seen the movie Gravity, right? So this first scene where they're flying through space, right? We don't want that to happen. So how do they train the astronauts? Well, they have huge pools. This is one in Johnson Space Center. There's also one in Russia, where the astronauts are submerged in basically aquatic equivalents of their spacesuits. And also submerged with them are life-size replicas of the spacecraft. And they also have support divers there for safety. And they essentially practice the things that they'll have to do when they go into space. All right? And so this is referred to as neutral buoyancy training. And it amounts to an altered sensory environment, right? And that's one reason why this is done underwater, to get some familiarity with that feeling of weightlessness. It's similar to space because the weight of the limbs and the weight of the body is offloaded. And scientifically, we talk about a lack of proprioceptive cues to the direction of gravity. Proprioception is the tension in muscles and joints. And also a lack of somatosensory cues to the direction of gravity. Somatosensory is just pressure on the skin, right? As I stand here, I have the force of on my feet, and I know how gravity is oriented. But it's different from space. I mean, gravity is still present, obviously. In particular, the vestibular organs in the inner ear can continue to tell you where gravity is, even if you're underwater. And you also have the resistance of the medium that you're in, right? Being in water is different than being in the vacuum of space or being in air. And so that's a little bit different. So our motivation was twofold, right? First, we wanted to see if we can reduce the costs of this kind of neutral buoyancy training. Instead of having a huge facility like this one, with 4 divers per astronaut and replicas of spacecraft and things like that, maybe you could do something that works almost as well, just using virtual reality. So that was one of our goals. And then the second is to evaluate how using VR in this altered sensory environment actually affects people. And it should affect people because the things I talked about before, you don't have contact with the support surface, you don't have these somatosensory and proprioceptive cues, but you still have the vestibular cues. So this unique combination of sensory stimuli, how does VR affect people in this environment, right? That was the second goal. So a little bit of background, what's been done that's similar. Well, it's no secret that NASA already uses virtual reality to train people. In fact, NASA's virtual reality lab, they have a spacewalk simulator where you have a controller that is very similar to the controller shown here, joystick. It's a replica of the one for the actual device. Their jetpack is called SAFER, Simplified Aid for Extravehicular Rescue. And so there's a simulator where you can go in, take this joystick, and have some feeling of using the controller to move around space, right? NASA also has a hybrid reality lab, and they've developed a simulator for what is the more common method for getting around on the outside of the spacecraft, which is handrail locomotion. So these jetpacks are really just for emergency use. Normally the astronauts kind of use their hands to move around the outside of the spacecraft. This is a picture of the Argo system. This is active response gravity offload system. So it's a system of cables that sense where the pressure is and adjust the support so that you have this feeling somewhat like weightlessness, right? And then finally, NASA, in collaboration with the Navy, is working on an augmented reality display for use both underwater in a kind of a rigid underwater helmet like this, but also ultimately they want to use something like this in the next generation of spacesuits. So this is similar research that's been done in the past in terms of space-related VR and AR. There's also been, of course, prior efforts to develop systems for using VR underwater, and so that's what I'm showing here. The ones in the upper left, Quarles et al. Developed an application called Shark Punch, where this was for rehabilitative purposes. You're underwater and sharks come at you and you have to punch them. So it's essentially a waterproof head-mounted display. Zhang et al. And Osoni et al. Also developed an underwater or waterproof head-mounted display, mostly for snorkeling. And there's now a commercial, there's now a company, Ballast VR, that has developed these waterproof head-mounted displays for use in water slides and also snorkeling, so you can have kind of, virtual snorkeling over the Great Barrier Reef kind of thing. This Hatsushika et al., they developed a PC VR implementation, so you have the advantages of more computing power, and that's specifically for scuba training. The disadvantage is that, of course, you're tethered in their implementation. You have some cables that are going up to the surface. And ours fits into this kind of matrix here. It's a mobile VR solution, but specifically for use while scuba diving, because we wanted people to be neutrally buoyant, not on the surface, under the water, right? Not on the bottom of the pool, not on the surface, but in the middle. And really, what we wanted to do, the thing that is maybe most unique about our efforts, is that we wanted to really try to evaluate VR use underwater. So a lot of these other studies are mostly about developing the technology and not about looking at kind of sickness and presence when using VR underwater. So that was one thing we wanted to do. Okay, so to develop the headset, we identified this full-face dive mask here. This is an OTS Guardian, Ocean Technology Systems. And one reason we chose this one is because it has a removable visor, right? So the idea was we take off that visor, we generate something similar, modify it, and put in just a smartphone and lenses. As an input device, ideally we would have taken something like this, which is the controller for the Safer system. It's a 3 degree of freedom joystick, and there's a little switch on there. You can control rotation or translation. And there's also a button for motion nulling. Problem is that these things cost, I think, $100,000 or more, and NASA wasn't willing to give us one. So we decided to just use an Xbox controller because you can, there are joysticks on the controller. It's just a joystick, right? And we thought this has the advantage that people coming into our experiment would be familiar with it. They would be able to use it without much training. So this is an overview of what the hardware looked like altogether. You have the mask, you have the visor, which is now modified to accommodate smartphone and lenses. You have the controller there, and the controller was waterproofed inside of a latex bag. This is a breathing bag that's made originally for purposes of anesthesia. And there were a few iterations. We settled on this because the latex actually preserves a quality of haptic interaction with the joystick, right? As any of you who have done this kind of thing know, there were many iterations of this to try to get it right, get the ergonomics, try to get the phone so it's not slipping out, get the phone and the lenses positioned in the right place so that people with different shapes of faces can actually use it. So this was, we had to go through a few iterations here. And this is what the final product looked like. So on the left is a view of looking into the mask, and on the right is the view of the mask with the controller attached. And we programmed a spacewalk simulator. We used assets for the Earth and Sun and the space station. And this was all programmed in Unity. There was also the body of the astronaut, so you could look down and you could see a virtual version of your body. And the task people had was to navigate through a system of gates, floating green gates in space. Use the jetpack to control your 6 degrees of freedom, move through those gates. Details, we implemented the real physics of the system. So the spacesuits are very heavy, 300 kilos. Translation, it generates 14 newtons of thrust. Rotation, 2.2 newton meters of applied torque. This results in linear accelerations of about 5 meters per second squared, angular accelerations of 2 to 3 degrees per second squared. So not strong accelerations, which is actually good for avoiding making people sick. And we use the left joystick for rotation, the right joystick for translation, and we implemented this motion nulling that NASA also has. If you push the joysticks, you could stop your motion in space. NASA only does the nulling of rotation. They don't do the nulling of translation, so we added that just for ease of use. Evaluation. The study was conducted at our local pool, the university pool, down in the diving end, the deep end there. So we rented space. And it was a little bit of a trick to get the human subjects approval for this one. When you tell people that you want to put an electronic device on people's face and put them underwater where they can't see, they start asking questions, how are you going to make this safe? And I'll tell you guys a little bit more about that. And we were able to borrow equipment free of charge from a local dive shop, which was really nice of them. So as I said, the task was to navigate through these floating gates. They had to do 6 gates per block. The gates were about 10 meters away. We always had a companion diver in the pool for safety, and also to help people maintain neutral buoyancy, right? To make sure people didn't float to the surface or sink to the bottom. We had a companion diver in there. Participants had to be scuba certified, and they had to report no history of visual or vestibular deficits. I mean, they could wear contact lenses, but otherwise no visual or vestibular deficits. And also, we had a kind of a training session, and some people we realized, okay, they can't do it, we'll get someone else. So there were some people that came in and didn't end up participating. And our dependent measures are essentially time to completion, getting through, how long does it take people to get through the gates, measures of sickness, measured through the simulator sickness questionnaire before and after, and also the presence questionnaire. So this is a schematic of the experimental design, right? We had a familiarization phase where people came into the lab. They filled out the SSQ. EVA stands for the extravehicular activities. That's the spacewalk. They went through 6 gates. And after they completed that, simulator sickness questionnaire again and the presence questionnaire. Then on a separate day, they came back and they did the underwater phase. Simulator sickness questionnaire. The underwater phase, they completed 3 of these blocks of 6 gates. And then again, simulator sickness and presence questionnaire. And so you're probably wondering what the experience was like, and that's what I want to show you here. So this is just getting the diver ready. And now the subject is underwater. You see the companion diver that's helping them maintain neutral buoyancy. This is the view that you have from inside of the app, right? You're looking down, you see your virtual astronaut body. There's the green gate that you see in front of you. The space station there, the Earth is off to the left. So you can look around, you can see the Earth, you can see the sun. And people are using the controllers to move around. You can see the person is slowly approaching this gate. So they're applying some linear thrust to move through the gate there. So they've achieved the first gate, and then again another one pops up and they have to do another one and another one. So that's that was what the experiment looked like. So what did we find? Start off with the time to completion. So on the left, in the black, is the familiarization. How long did it take them as they were sitting above water in the lab? On average, it took them more than about 2 minutes to go through each gate. But then as underwater, you can see that, with repetition, the time to completion was getting shorter and shorter. So people were getting better and better. So they were actually learning to use the jetpack locomotion, which was one of the things that we wanted to show, that you can do effective training in this environment. Not an unexpected finding, but we wanted to show that anyway. Really, we wanted a task that would allow us to assess the sickness and the presence, and that's what I'll show you now. So here are the results, the sub-scores for the three different sub-scores for the simulator sickness questionnaire. Nausea on the left, oculomotor in the middle, and disorientation on the right. And the only one that showed significant difference was nausea. So pre minus, post minus pre, there was an increase in feelings of nausea and discomfort after the underwater, but not for the others. And I want to talk a little bit in the discussion about what we think is going on there, or actually the fact that we don't know exactly what's going on there. Here are the results of the presence questionnaire. The total scores are on the bottom here, and you can see there's a slight increase in presence in the underwater compared to the familiarization, but none of this is significant. Sub-scores for realism, possibility to act, quality of interface, etc., no significant differences. This is despite the fact that people actually reported to us that they felt more immersed, not just submersed, but immersed in the underwater environment. So, okay, so what can we take away from all this? In terms of sickness, we found this difference specifically for the nausea. But there are a lot of things that could explain this difference, and so more research is needed. It could be that just being neutrally buoyant causes you to feel more discomfort than otherwise, right? We need some kind of control experiment where we have people fill out a simulator sickness questionnaire, go underwater without VR, and then fill out the simulator sickness questionnaire. Maybe it's just that. Maybe it's breathing the compressed air that's causing some sickness. We also had a flaw in our experimental design. People were doing 3 times more trials underwater than above water. That could be a factor. And we also had an issue where the screen would vibrate when people breathed because the mask is attached to the face. The screen is attached to the mask. This vibration could also have been playing a role. So we found more nausea-related symptoms, but we don't really know what's causing that. So anybody who's enthusiastic about underwater VR, don't be alarmed. There's still hope. Right. Regards to presence, we were expecting to find more presence underwater. The idea being that VR can be a multisensory experience, and here we're adding factors that are more consistent with the virtual environment being in space. And as I said, we had these anecdotal reports that people felt more immersed and more present, but we didn't see that in the questionnaire. And that leads us to think maybe we should be asking different questions, right? This questionnaire has questions such as, how did your actions in the virtual environment compare to when you do those actions in real life? Well, nobody's ever been into space, right? So they can't really answer that question. So in retrospect, I think we should have had some other questions in there, like, what was your experience of weightlessness? Things more catered to this particular environment. So things we would improve in the future. As I mentioned, we had this vibrating of the display. This is because we had a full face mask. At first we thought it was just the phone vibrating around in there. It wasn't fixed. In the end, we realized the whole mask was moving when people breathed. And we chose the full face mask because we wanted to allow people to talk. You can actually talk underwater if you have one of these full face masks, so it's good for communication. But we're going to have to figure out a solution to this vibration of the display. Maintaining neutral buoyancy. Some people reported that the bubbles coming from the companion diver were distracting, right? The diver was right underneath them. So it would be nice to have a kind of a more automatic method for maintaining neutral buoyancy rather than what we had. Conflict. When people moved with the jetpack, they weren't actually moving in real life. And so for the linear, this is not a big problem because the accelerations were very small. So there wasn't really a detectable conflict there. The movements were below vestibular threshold. But in future, it would be good to have methods to track people underwater. How can you take some of the tracking technologies that work above water and use them underwater? And then for the angular, those movements were above threshold. It might be nice to implement a way to have people actually move, right? Like have an aquatic jetpack, to actually move them consistent with the controls that they're giving. You could do that by moving the people, or you could just generate currents that make people feel like they're moving, right? You could move the water instead of the person. That would be one thing. Other things, bringing parts of the body into the environment, tracking the hands, bringing the hands in. Having actual haptic interaction. So what I mentioned, this hybrid reality lab, they have VR headsets. You can interact with real objects. Those real objects are brought into the virtual environment. And that would add to the realism and also make it more effective for training, right? Using tools, doing the tasks that the astronauts have to do typically. And lastly, there's a need for good methods for wireless communication underwater. So Bluetooth and Wi-Fi don't work very well underwater. And so ultimately it would be good to implement those. So I think there's a bright future for underwater VR for a variety of applications: entertainment, scuba training, astronaut training. There are many ways to improve the experience, and obviously we need more research on sickness and presence in these altered sensory environments. So in the end, I want to just thank all the people that collaborated. We had a big group, and thank you for your attention.
Questions?
I think this is amazing. I have a few questions. First of all, what's the maximum depth that you can go on this configuration?
I don't, so it's limited by the mask, right? Assuming that we got a good seal between our visor, our made visor, and the rubber seal, you could go as deep as the mask is rated for. I'm guessing at least 100 feet, 30 meters. Typical masks go that deep.
Probably. You won't have problems with pressure?
No, I mean scuba divers regularly go down to 100 feet, 30 meters. So, and our seal should be good because what we did is we 3D scanned the visor and then we modified it and then printed it. So the shape of the visor that we had in terms of the interface with the rubber was identical.
And you think that this solution would work in OpenSea?
I don't see why not. The problem is knowing where you actually are in the real environment. I've done some scuba diving, and visual cues are really important. You look up to see where the surface is. You look down to see where the ground is. So without those, you'd have to have a way to bring that information into the mask, into the VR display.
Okay, thank you.
Yeah.
More questions?
I should say it would also depend on the strength of the 3D printed plastic that we have. It's as strong as the visor. I don't know that.
Just one quick question. In what you mentioned in terms of improvement, you never mentioned visual fidelity.
Yes.
Don't you think is a factor?
Certainly, yeah. So we used a mobile VR solution because we didn't want to be tethered. But if you could do PC VR, then you could have all the advantages of PC VR. And as resolution and all the other things improve for displays, then that would also be a benefit for these systems. Yeah.
Any more questions? Huh?
So thank you. This is really amazing to see. One question would be, or maybe a comment regarding to the sickness. You mentioned a lot of effects and also things as vibration, but do you not think, because there's many external forces on the participant as such. So not only that you are unfamiliar with movement in water, also you have another person kind of stabilizing you, and you're steering, and not naturally, but with a joystick. I think this is the most impact on sickness to my regard. And the second question with regarding the presence questionnaire, did you actually perform a reliability analysis on this questionnaire? So did you check whether the questionnaire really assesses this construct reliable?
The reliability test, the reason we chose the presence questionnaire is because it's been used many times before, so we were kind of relying on that. Going back to your first question about the sickness, I agree with you completely. The sickness can be caused by various things, and really we need to do these controls to rule out, systematically rule out the different things. So comparing the above water with the underwater, this idea of moving unnaturally with the joystick, you have that above water and you also have it underwater. So that comparison should allow you to address at least that question. But I totally agree, you know, there's a need to kind of go through here and see try to tease it apart for further experiments.
Very good questions. Thanks for the talk. I'm just curious because a lot of the NASA training, they expect their astronauts to barf a little bit once they go up, and especially with the spacewalks as well. Like in some of the interviews, you hear them like they're trying not to because it's a really bad situation. But how would you be able to tell apart that? Let's say you have increased fidelity in terms of interaction, in terms of visual fidelity, and everything.
Yeah.
How do you tell apart that this is not actually the same kind of sickness that you would experience if you were actually on the spacewalk?
So there is sickness when you go into zero gravity, and that's more related to the kind of the offloading of the vestibular system. Because when you turn your head in space, you no longer have those gravity heads turning as you would, gravity signals turning as you would expect them. And so that's I think that's one of the big reasons that astronauts get sick when they go into space and also when they come back. It's that adaptation to zero gravity on the vestibular system and back. So we don't have that here. Yeah, you don't seem convinced, but
No.
Yeah.
I was just thinking, like, do you, because you still have the gravity affecting in the water still?
the gravity is still so the stimulation to the otoliths in the inner ear is the same.
Okay.
For underwater and above water, and I think that's a thing that causes sickness going into space.
Thank you.
Yeah.
Last question.
Just a quick suggestion. So one of the cool techniques we have in virtual reality that you can use to avoid using the joystick is reorientation when the person blinks, right? So there is work that something like 22 meters is enough to cover an infinite space. Something for you to consider because you have the entire pool for yourself. So instead of moving via joystick, people would be moving as if for real.
Yeah.
In this space, and you would just slightly turn them when they blink.
Yeah, that's a nice idea. We also thought about kind of repositioning people with jets, right? So you move a certain distance and then you slowly drift back, right? Something you can do in underwater that you might not be able to do above water.
Okay, thank you very much for the interesting talk.